Hello friends, welcome to Electronic Circuit Hub. So today I'm gonna design overcurrent limiting circuit using some discrete components. Okay, I'll explain how you can design the overcurrent limiting circuit for your linear regulator, and I'll also run the simulation and I'll show you the voltage and the current waveforms at different nodes. Okay, so in the last video I have explained about the designing of linear regulator using some discrete components. So in this video I'm using the same circuit what I have used to design the linear regulator, okay, using discrete components. So if you haven't watched that video, I highly recommend please go and watch that video first so that you will understand this video how I'm designing overcurrent limiting circuit for your linear regulator. Okay, so I'm using the same circuit here, and if you look at these two components RS and Q3, this is the only additional circuit which is helping me to design the overcurrent limiting circuit for your linear regulator. I'll explain how this circuit, how these two components help in order to design the overcurrent limiting circuit or in order to limit the overcurrent in load overcurrent or any short circuit current. I'll explain this. So let us first understand about this circuit and later let us understand the role of these two components Q3 and RS here. Okay, so if you look at input, so what my objective here is I want to design from 24-volt input to 12-volt output and 80 milliampere load current. So if you I write here my load current is I naught, I call it I naught, and it is, let's say, 80 milliampere more or less. Let us assume for now, and the input is 24 volt. So what I'm doing here is I'm changing, let's say, a fixed value. I'll recommend you to use the fixed value. Let's say this is the, I'm using DC, and let's assign some value for DC, that is 24 volt. I'm not changing here any input voltage, so this is 24 volt. And if you look at this Q1 is series pass transistor, and if you look, this R1 value is 10k, and the current flowing through IR1 equals to IB, the base current flowing through Q1 and the collector current flowing through the Q2. And if you look at R2, this is also K2, which helps to limit the current flowing through this Zener diode. So in the last video I have asked, I've got many comments why you are using this 6.2 volt Zener. So to answer that question, if you look at the library of LTSpice, and here I see the minimum Zener breakdown voltage, what I found is 6.2. If you look at 8.2, 10, 12, 15, so minimum Zener voltage I found is 6.2. So that is why I use D1 6.2 volt Zener. Okay, and if you look at R3 and R4, these are the feedback resistance which helps to get the stable output at stable output, okay, 12 volt. And now let me explain, this is the load resistance value R5, which is 150 ohm. Now let me explain the why we need the resistance RS of 8.25 ohm. Okay, so how will you calculate the value of resistance RS? In order to calculate the value of resistance RS, you can apply this formula. RS equals to VBE sat divided by I naught. I naught is the output load current, rated load current, and VBE is the saturated voltage, saturation voltage of Q3. So you can fix the resistance value of RS based on your VB sat value of your Q3. Okay. So once you do that, now let me run the simulation and let me show you how this circuit simulates and how you can see the different waveforms. So I'll run the transient analysis. I'll go the window, tile window vertically, and let me show you the first input voltage. This is fixed 24 volt, And if you look at output, if you look at here, you see you have around the 12.17 volt at output. And if I click on here current, you can see the current is around 81 milliampere. Okay. So what you can see here, your input is 24 volt and your output is 12 volt and 81 milliampere. Okay. Now what I'm going to do is, in spite of using 150 ohm resistance, let me use 1 ohm resistance. So I directly right away place the 1 ohm resistance. Okay. And let me run the simulation again. So what do you see here, guys? Now what I've done is, in spite of using 150 ohm, I have simply used 1 ohm resistance. That means I am trying to short circuit your output. Okay, let me see what happens. So if I short circuited my output, if you look at here, the I'm getting here V out. This is my V out, and let me divide into two plot pane. This is my V out, and let me show you here the I naught. Okay, so if you look at here, my V out is 90 millivolt, and you can see my output current is, even you have short circuited, it is limited to 90.5 milliamps. That means what do you understand by this? That means that if even your load is short circuited, you are drawing very high current, high load current, but still if you do the math, 12 divided by 1 ohm, that means 12 ampere current is flowing. But what happens is, if you look at in your simulation, your output voltage drops rapidly to 90.5 millivolt. So your output current is 90.5 milliamps, and your output voltage is 90.5 millivolt. So that is how y- so the selection of this RS is very critical. So you have to select RS very carefully. And if I want to show you the voltage across base to emitter of this transistor, if you look at this VB, and it is around VB is around, if you look at it, 640.7 millivolt. Okay, so let me show you how much voltage drop across. Let me delete this all the things now. This, the load current I want to delete, this also I want to delete. Let me show you the voltage here. Let me go at window, child window vertically, and let me show you how much voltage dropping this Q1. Okay, you can see out of 24 volt, Q1 is dropping 23.2 volt. And what is the voltage drop across here? If I want to show you, the voltage drop across here is 1.6 volt. And if you look at the current here, this is 88.3. If you look at the load current, it is 90.3. And if you look at here, the I'm not sure how I can see the collector current. I see Q3 is 2.1 milliampere. Okay, so your output current is 90.5 milliamps and your output voltage is 90.5 millivolt. So guys, I hope that you have understood how you are going to design the overcurrent limiting circuit for your linear regulator. If you're designing your linear regulator using some discrete components. If you have any further question on overcurrent limiting design, feel free to ask me in comment section. Thanks for watching this video.